Hi everybody, Mr. Fig here. I just wanted to do a quick demonstration of polarization. But before I talk about polarization, so a quick little review. Remember that we described light, the direction light travels by drawing an arrow representing a light ray, and that all light travels at 3 times 10 to the 8th meters per second. And here when we say light, we really mean anything in the electromagnetic spectrum. It could be radio waves, microwave, gamma rays, doesn't matter. All light travels at 3 times 10 to the 8th meters per second, at least through the vacuum of space. Okay? But although we represent light using an arrow to show its direction that it travels, light itself, it's important to remember, is really a wave. In fact, the light wave is made up of 2 parts. A light wave is made up of a vibrating electric and magnetic fields. Now, we'll talk about electricity and magnetism later in the year, but the important thing to know that, remember that if the light is traveling in this direction, then both the electric field and the magnetic field are vibrating perpendicular to how it travels. That means that light is a transverse wave, as we talked about before. But the interesting thing is, only the electric part of the light wave strongly interacts with atoms. That's because the electrons, which are negatively charged particles, are always on the outside of atoms. So when we talk about a light wave, we usually only consider the electric part, and we kind of ignore the magnetic part because it's the electric part that's most strongly interacting with atoms. So what we're talking about today is polarization. Now, a polarization filter only allows light through if the electric part points in the correct direction. Now, I'll show you some of my polarization filters in a second, but here's a simple representation. So here, if my electric field is vibrating up and down to the way the light's moving, and my filter is also set up and down, so that light ray can go right through because the electric part points in the right direction. But if I rotate the filter so the fence lies sideways, when this light ray tries to come through, it's going to be blocked. Okay? So, but let's take a look at it in the real world and see what polarization filters really look like. So here's an example of a polarization filter. It's a piece of plastic, which is made out of long, thin molecules, and they kind of act as slits of a fence. Now, I've drawn an arrow to represent, a double-sided arrow on this piece of plastic to represent which way the filter goes. And I have another filter here, which I've done the same. Now, the first thing you'll note that if I place one filter over this post-it note, you'll see that the light comes through no matter how I place the filter. But you'll also notice that it's dimmer. That's because the filter is only letting through light with the electric field in one particular direction. So some of the light is being blocked. Now, what's interesting is if I put a second filter over the first. If I keep the arrows lined up in the same direction, that you'll notice that we can still read the words underneath the 2 pieces of plastic. But watch what happens if I rotate the filter. Now suddenly the image is blocked. Again, this first filter only allows light vibrating in this direction. So this filter, where I have rotated, only allows light in the up and down direction. So there's none of that light is left. All the light coming through this filter is polarized, so the electric field is vibrating back and forth this way. So here the light's let through. Here the light is blocked. I'll demonstrate it with this little toy jack that I borrowed from our cat. There you go. Again, one filter I can see the jack. If this filter's in the right direction, I can still see the jack. If I rotate it, the image is blocked. No light will come through. Now, again, this technology is often used in the movie theaters to mimic 3D. So when you go to the movie theater, generally when you're wearing your 3D glasses, one lens is set to be polarized in one direction, and the other eye is set to be polarized in the opposite direction. If you've ever looked at a 3D film without your 3D glasses, you'll see that there's actually a double image. You're actually watching two movies at once. One designed to be broadcast to the left eye, one designed to be broadcast to the right eye. And because the filters are set up a certain way, that is fooling your brain thinking you're actually seeing something in 2D. All right, I hope you've enjoyed this quick demo. I'll get this posted on the website. I'll talk to you later. Bye.